Welcome back to Meaning from Data, Statistics Made Clear. As you recall, we're in the midst of a 4-lecture sequence about how to describe, summarize, and organize data if we have all the data in the population with which we're interested. In this lecture, we're going to talk about a fundamental strategy with which we attempt to understand our world. And that is by identifying examples of cause and effect and other cases where two varying quantities are related to each other. And this comes up literally all the time in physics. You hit a ball and it travels in a certain predictable trajectory. If you put a hot object in the room, it's going to cool at a certain rate. If you bend a lens at a certain way, it's going to focus the image at a certain distance. So those are examples in physics of correlations between one thing and another. In everyday life, social situations, you have lots of examples of cause and effect. If a student studies more, that student may possibly do better on the next test. Income of a person is related to the amount of education that they have. But you could certainly ask the question of whether the increase in the income is a result of the knowledge or skills they gained from education. In seeking a cause and effect relationship, maybe the education actually allows the person to be more productive, actually able to do things that allow them to make money, but maybe it's really other factors that demonstrate that correlation that has nothing to do with the actual acquired skills of education. So in any case, in all of these examples, whether it really is cause and effect or just moving together, what's involved is a pair of numbers or qualities that each member of the population has that we're trying to compare. If a cause and effect relationship actually is operating, then the two features or the numbers that describe the features will move together. The manifestation of cause and effect will often be a list of pairs of numbers. And the first numbers will have some relation, the first in the pairs will have some relation to the second number in the pairs. So in this lecture, what we're going to do is try to identify and describe the relationships of pairs of numbers. And statistics is a tool which we're going to try to develop. We're going to, in this lecture, develop concepts by which we can look at a list of pairs of numbers and decide whether or not there really is some relationship to how those numbers are moving. So there may be a relationship, by the way, whether or not there is a direct causal reason for one thing to be moving in a way similar to the other. And it can often be a real challenge to distinguish between a cause and effect relationship or just another kind of correspondence that where actually cause is not involved. I'll give you an example. There's certainly a correspondence between SAT scores of incoming college freshmen and grade point averages. But it's not true that getting a higher score on one's SAT actually causes the student to get a better grade. In other words, the grade is not computed by saying, okay, what was your SAT score, therefore you get a better grade. So it doesn't cause the higher grade, but nevertheless, a person with SAT scores higher often gets higher grade point averages. So the two quantities exhibit a correlation, meaning that they move together, but neither one actually causes the other. So a goal of statistical analysis is to see whether two quantitative qualities of members of a population are correlated, that is, move together. And we should say now that the question of causation is really outside the realm of statistics. Statistics results certainly can be adduced to bolster an argument about causation, because if you are claiming there's causation, you should be able to find evidence that has two things that are moving in step. But it's not, but statistics' job is to measure to what extent they're moving together, not to say whether or not one is causing the other. That's a different question. So the first step that we want to take in discussing these pairs of numbers and seeing whether they move together is a visual one. Let's see how we can represent pairs of numbers in an effective visual way. So here is a visual representation of such a phenomenon. Namely, this is a description, a visual representation of data about a bunch of students. Each student is represented by a dot. And the dot is placed for each student by looking at the SAT score of that student, and then moving up on the line to where the grade point average of the student is in college. So this is the SAT score, which was a test taken before college started, and this is the college grade point average after the student has been in college. So this is sort of a cloud of dots. And you can see that this cloud of dots generally moves up as you move to the right. In other words, higher SAT scores seem to be associated with higher grade point averages. But certainly the dots don't lie on a perfect line by any means, as you can see, because not every student with a particular SAT score is going to get that particular grade. And getting a higher SAT score doesn't guarantee, as you see, doesn't guarantee a higher grade. See, this person got a 1200 SAT, but has a 1.8 grade point average, whereas this one had less than 1000 SAT, this person right here, and has a 3.5 grade point average. So it's not at all a perfect correlation. Well, we're going to try to quantify the extent to which these two variables are related by giving a number, defining a number that's called the correlation, that summarizes the extent to which these two varying quantities, in this case SAT and grade point average in college, are moving together. When one quantity increases, we want the other quantity to tend to increase. If when you increase the SAT, you increase the grade point average, that's called positive correlation, when the cloud goes up to the right. If you have the opposite, that is when you increase one value, the other one goes down, then that's called negative correlation. So SAT scores and grade point averages, they are examples of a positive correlation. An example of a negative correlation would be that if you look at the amount of, say, the number of cigarettes a person smokes versus their life expectancy. Well, that would be a negative correlation. The more cigarettes, the lower life expectancy. So it would be a downward cloud. So a scatter plot it is the first thing that we're looking at, and it gives a visual representation of the concept that we're trying to get at, whether the cloud is moving together. Well, we're going to next think about trying to develop a formula for correlation. And the way that we are going to develop this formula is to first look at the two varying quantities individually. In our example, we'll look at the SAT scores individually, and then we'll look at the grade point averages individually. And by looking at them individually, we can do things that we've done in the previous lectures. We can compute the mean of the SAT scores, and we can compute the standard deviation of the SAT scores of this collection of students. And for example, let's just look at our example here. In this example, the mean of just the SAT scores, that is how these scores here, the mean of those scores turns out to be 1070. That's the mean. And the standard deviation is 163. So remember, the standard deviation is some measure of how, on average, how far apart a typical score is from the mean of the whole population. So there are some students who have a score that's, say, 1 standard deviation above the mean, and that would be the sum of the mean plus the standard deviation, 1233. So a person who got a SAT score of 1233 would lie somewhere on this line here. It would be a dot above this line. Now, the grade point average can be looked at individually also. So the grade point average has a mean of 2.6, and its standard deviation is 0.78. So the mean grade point average is something, 2.6. Standard deviation, the amount of spread in the grades just viewed by themselves, is 0.78. So the strategy by which we think about this concept of correlation is really to ask a question about whether the student's grade point average is how closely it's associated with the SATs, and it's measured in standard deviations away from the mean. In other words, you see, if you have a student whose grade point average, whose SAT scores was 1 standard deviation from above the mean of the SAT scores, you're going to ask the question, is the student's grade point average 1 standard deviation above the mean of the grade point averages? In other words, in this particular case, where if you had a student with a standard an SAT score 1 standard deviation above the mean, we saw before that student would have scored 1233. Of course, it wasn't really 1233 because SAT scores just always end in 0. But if you had a student in that range of about 1233 SAT score, then you're asking the question, would that person's grade point average also be 1 standard deviation above the mean grade point average, which would be a 3.38. And if so, then we're having a correlation between the two, because their distance above the mean measured by standard deviations above the mean, which you may recall was called the z-score of that datum, how many standard deviations away from the mean it was. That's the way we measure the units of in comparing, in this case, SAT scores with grade point average. Because you see they're on different scales. The numbers aren't the same. SAT scores are 1,000, and GPAs are some number between 0 and 4. So that's the way to make sure that the units can be compared. Well, we'll say that a data set is perfectly correlated if the distance from the mean measured in standard deviations of the one variable corresponds exactly to the number of standard deviations above the mean of the other variable. So let's give some examples now. So a perfect positive correlation then would draw a figure where the scatter plot really consisted of an exact straight line. All the dots lay on a straight line. That is a perfect positive correlation. A perfect negative correlation would occur when all of the dots lie on a straight line, but heading down instead of up. So this would be a case that we could rephrase by saying that the z-score for this variable is always the negative of the z-score for the vertical variable. Now let's look at the definition of correlation and to try to get a numerical measure for how it is we're going to compare the two varying quantities, the first and the second of these paired variables. Now, this, once again, has a sort of a formidable look to it, but let me just walk you through it and see what it is that all these symbols mean. The x's refer to the quantities that are changing. In the case of our the horizontal first component of these paired variables. So the x's in our previous example would be the SAT scores, individual SAT scores. And x bar, you may recall, was the mean of the whole set of, in this case, SAT scores. So, and then s sub x is the standard deviation of the horizontal value. So this S sub x is the standard deviation, and you can see that actually when you take the difference between a value and the mean and divide by the standard deviation, all that's telling you is how many standard deviations away from the mean you're getting. So if this difference, for example, were 1 standard deviation, then then the difference would be equal to 1 standard deviation, and so when you divide by the standard deviation, you'd get 1. So this is really just the way of saying that this is what we called before the z-score, the number of standard deviations away from the mean. Likewise, this second fraction here is measuring exactly the same thing for the second component number of this pair, the number of standard deviations above the mean for the vertical axis collection of data. We multiply these two things together, the z-scores from each, and add them up. Remember, this capital sigma just means add up all of the values that we get going from throughout all of the data. And then we take sort of an average. It would be an exact mean if we divided by n, because you have n data points. Instead, we divide by n minus 1. It's a slightly technical reason why we divide by n minus 1 instead of n. But the answer, morally speaking, this is just the mean of it's an average, the mean of this product. And this is traditionally called R, and this is the definition, the technical definition in statistics of the word correlation. So this is the correlation of two data sets, X and Y. And this is, these down here are just reminders of the definition of the standard deviations for the two data sets. Now, let's do a specific example so that we can measure what this correlation, what kind of a number it gives us. So let me do an example. So here's an example. We have, in this case, our example has four points to it. Here they are. And these are ostrich eggs versus ostrich hens in a ostrich farm. You see 4 ostrich farms. And this ostrich farm has 3 hens, and that hen laid 100 and some eggs, just a little over 100 eggs. And this farm had 5 hens, and those 5 hens had close to 200 eggs. This farm had 6 hens and had a little over 200 eggs. This farm had 7 hens and had 300 and some eggs. So these are ostrich eggs. See, you probably didn't realize that you would learn about ostriches in this lecture. And by the way, I learned that ostriches have on average about 35 eggs per year. And that's something you may not have known. Some people don't know that and seem to get along perfectly well without knowing that, apparently. So here are the different farms. We have the number of hens in each farm, and then down here we have the number of eggs that each one produced. And we deal then, again, the farms individually, that is the number of eggs per farm. We have a mean of 5.25 hens per farm. And then here we have the mean of 209 eggs per farm. And so we do the calculation for associated with finding this correlation, which means subtracting each number from the mean. So we have 3 minus 5.25 gives negative 2.25. Remember back here, I'll go back to our formula, which you see the first thing you do is you subtract. For each value, you subtract the mean. So we subtract, we get these values, we get the difference in the y's from the mean, we find the z-scores. These are the z-scores for each one. And when we take the z-scores, we multiply the z-scores together, we add them together, we divide by n minus 1. Remember, 3 was, we're dividing by n minus 1. We have a total of 4 farms, so we divide by 3, and we get 0.92. So the correlation of this data set then is 0.92, which means geometrically that the data lie pretty close to a line, that we can draw a straight line and the data points are pretty close to that line. And the higher correlation closer to 1 is corresponding to a higher data point. So the first thing to know is that correlation always produces a number between 1 and -1. All that complicated stuff, you take all the z-scores, you multiply them together, and you add them, and then you divide by the thing. It turns out it always gives a number between 1 and -1. It's not obvious why it does it, but it is true. And if there's an exact correlation between the two things, either positive or negative, then the correlation will be +1 or -1. It's +1 if the data lie on an exact straight line. If the correlation is -1 if the data lie exactly on a straight line that's descending. So those are the two extreme cases. And now let's look at some examples where we have a correlation that's between the two. Now here's an example that I found interesting. This is an example that is comparing, in a population of adult men in the United States, it is comparing the weight of the men on this axis with their thigh circumference in this axis. Now, the reason I find this sort of interesting is because, and by the way, so let me first say that you can see that there's a strong correlation between these two measures. In other words, for heavier men, their thigh circumference seems to be increasing at almost along a straight line here. See? So instead of weighing yourself, what you could do is just measure your thigh, you see, and you get a pretty good estimate for how much a person weighs. The reason I'm sort of surprised at this is that it seemed to me that the thigh, since it's just the circumference, you'd think that there would be like a cubing issue involved, that if you increase your weight, your thigh by a little bit, that really increases your radius of your thigh, and you'd think you might sort of square maybe your weight instead. But these are the facts. We cannot dispute them. So the correlation here is 0.87, meaning that these data do lie more or less close to a straight line. Let's look at some other examples. Here's one where the correlation is not as strong. It does seem to be going generally up to the right, but you can see that no line that you chose gets the points clustered very close to that line. Here's an example where the correlation is a negative correlation. You can see that as the scatter plot tends to have the points going down to the right, and if you draw any line in there, they're quite close to the line, but not exactly on it. Here's an example that was obtained by simply taking random numbers. So we let the computer simply take random numbers and plotted them, and it has a correlation very close to 0. So a 0 correlation just means something where there's no real predictive value of one of the components, the first horizontal value of each pair with the second. They just sort of are random, and then you can see that. The measure of correlation is the technical definition of correlation, as all mathematical and scientific terms, has a very specific meaning. Often mathematics or science attempts to capture ordinary experience. In this case, we're trying to capture the idea that two things are moving together. But then we made a technical definition that talked about that. And the technical definition, to some extent, captures our human interest in that word, in that concept, but to some extent it doesn't. Once you've made the technical definition, you have something whose meaning you must then cope with in its own terms. So here's an example where the English meaning of the term may differ from what you may not feel this was a good thing to call, in this case, correlation 0. So let's look at this example. This is an example that has exactly 6 data points. 5 of them line up completely perfectly. 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. These are exactly on a straight line, perfectly correlated. But then there's just one more data point. Here it is. Now, the correlation of these data turn out to be exactly 0. In other words, if you plug those numbers into the formula for correlation, you get 0. Now, do we, in the human way, want to say that those two things have correlation 0? Well, in English, in regular life, you probably would say, look, there's a lot of connection between those data. Because for 5 out of the 6 of them, there was a very, very close connection. They were identical to each other. So this is a cautionary note to realize that there's nothing magic about mathematics. There's nothing magic about statistics. The reason for doing these, defining these concepts is to capture some idea, but it may or may not capture the idea that you want perfectly. And then you have to use judgment when you apply the idea. There's a wonderful example about correlation that is a very interesting, particularly for a person of my age and gender. In 1969, the Vietnam War was raging, and there was a draft lottery. The lottery was conducted in the following way. It was conducted in 1969 to determine who would be drafted into military service in the next year, 1970. And the way it worked was very simple. There were capsules made for every day of the year, every possible birthday, January 1st, January 2nd, January 3rd. These balls were put into a container. It was shaken around, and then somebody reached in and took out the capsules one at a time. And the first one that came out, whatever the date was on that capsule, a person with that birthday would be drafted first, be susceptible first to the draft. And then they reached in, the second one was chosen. You follow me? So the idea was a way to try to randomize the order in which people would be drafted based on their birth dates. Well, here are the data. The data look very random, as you would expect. Now, so let me explain what this means. On the horizontal axis, it's the birth date. That is the day of the year, the numbered day of the year. On the y-axis here, it's the order in which it was selected from the jar. You follow me? It looks like it's a random collection. But if you put it into the formula, you discover that the correlation is actually negative 0.23. And negative 0.23 turns out to be an answer that is statistically unlikely to happen if it were truly random. It's unlikely to happen by true randomness. So this is an example where, in fact, probably the balls were not actually mixed up sufficiently. That the first ones were put in first, and when they were taken out, the later ones in the year tended to be taken out earlier. So this idea of correlation had a huge effect on a lot of people. And here you can see some examples that September 14th was the first day chosen, and my birthday, July 10th, was the 284th birthday. So I did not go to Vietnam. We've drawn in all of our examples, including this example of the Vietnam War, we drew a line that sort of captured how the data were moving. That line that we're drawing is called a regression line. It's a line in which it, in a sense, most closely approximates the direction of the data. And the way it works is this. For every data point, every dot, you look at the distance to the vertical distance to this approximation line. And you choose the line such that the sum of the squares of those distances is minimized. And that's called the least squares regression line. So there's a unique straight line that minimizes that sum of the distance of the sum of the squares. And the distance between a data point, the vertical distance between the data point and the line, is called the residual, because it's the extra amount, the part that is different from your summary line, the regression line. A regression line summarizes the data with one line. Sometimes you have more variables than just one explanatory variable. Instead of just the grade point average in the SAT scores to predict grade point averages in college, you might have other qualities about a student. You know their SAT score, but you also know their high school grade point average. So you could take both of those things into account and then use that to compare it to the grade point average. And having more information about the incoming student, those are called explanatory variables, to explain a response variable, the grade point average in college. And we can make a really attractive graph of this using a way of capturing what really is a three-dimensional object in the plane. Namely, we have the scatter plot as before with SAT scores on this axis and the high school grade point average this time on this axis. And now, instead of bringing the third dimension out, which conceptually it actually is, we just color the higher grade point averages with the reds and the lower grade point averages with the blues. And you can, therefore, this picture, colorful picture, has to be in color, shows you a way of talking about what's called multiple regression, where you have more than one explanatory variable that is explaining a response variable. Well, in this lecture then, we have discussed one of the fundamental ways of trying to understand our world, which is looking for the consequences of cause and effect. We looked at statistical correlation of two variables, and then we looked at this regression line, the least squares regression line, which was a way to summarize the relationship between two varying quantities. The statistical concept of correlation helps us to identify and quantify the extent to which paired qualities of members of a population are varying together. Correlation does not indicate cause and effect, but it does indicate an association. And one of the, by the way, the prime misuses of statistical information is to mistakenly infer cause and effect from correlation. I'll look forward to seeing you next time when we'll talk about probability.